Separately derived systems, or SDS, are electrical systems that are electrically isolated from other sources of power, which includes the utility grid. An SDS has its own grounding electrode system and is not connected to the utility grounding system. Non-SDS, on the other hand, are systems that are connected to both the utility grid and the utility grounding system, and they do not have their own grounding electrode system. Regarding grounding in SDS versus non-SDS, SDS requires its own grounding electrode system. This provides a path to earth for fault currents and static discharge. Non-SDS utilizes the utility grounding system as its path to earth. The determining factor in establishing if a system is SDS or non-SDS is whether the generator is connected to the utility system. If it is connected, the system is non-SDS. If it is not connected, the system is SDS. Switching the grounded conductor does not change whether a system is SDS or non-SDS. The grounded conductor is simply a path to earth for fault currents. A backup transformer is a transformer that isolates the backup power source, which is usually a generator, from the utility grid. Once the backup transformer is energized, the system becomes SDS. To reiterate, to determine if a system is SDS or non-SDS, you need to consider whether the generator is connected to the utility system. Switching the grounded conductor does not affect this determination. A generator can be used to create an SDS or non-SDS system depending on how it is connected. To elaborate, let's delve deeper into the practical implications and technical nuances of separately derived systems and non-separately derived systems. Understanding the distinctions between these two types of electrical systems is crucial for ensuring safety, compliance, and efficient operation, especially when dealing with backup power sources like generators and transformers. Firstly, it's essential to grasp the concept of electrical isolation. In an SDS, the power source, such as a generator, is electrically isolated from the utility grid. This isolation is typically achieved through a transfer switch or a transformer. The purpose of this isolation is to prevent fault currents from propagating between the generator and the utility grid, thereby protecting equipment and personnel. Secondly, the grounding electrode system plays a pivotal role in both SDS and non-SDS configurations, but it differs significantly. In an SDS, the generator must have its own dedicated grounding electrode system. This system consists of a grounding electrode, such as a ground rod or ground plate, that is connected to the generator's frame and neutral conductor. The grounding electrode provides a low impedance path for fault currents to return to the source, facilitating the operation of overcurrent protective devices like circuit breakers and fuses. In contrast, a non-SDS relies on the utility grounding system. This means that the generator is connected to the utilities ground through the service entrance. While this simplifies the grounding requirements, it also means that the generator is susceptible to fault currents originating from the utility grid. Thirdly, the presence of a transfer switch is often a key indicator of whether a system is SDS or non-SDS. A transfer switch is a device that allows you to switch between the utility power and the generator power. If the transfer switch is designed to isolate the generator from the utility when the generator is running, then the system is considered SDS. However, if the transfer switch simply connects the generator in parallel with the utility, then the system is non-SDS. Fourthly, let's consider the impact of switching the grounded conductor. As mentioned earlier, switching the grounded conductor does not change whether a system is SDS or non-SDS. The grounded conductor, also known as the neutral conductor, is the conductor that is intentionally grounded at the source. Its primary function is to provide a return path for unbalanced currents. While it is important to ensure that the grounded conductor is properly connected and sized, its presence or absence does not determine whether a system is SDS or non-SDS. Fifthly, backup transformers play a crucial role in creating SDS. A backup transformer is a transformer that is installed between the generator and the load. The primary purpose of the backup transformer is to isolate the generator from the utility grid and to provide voltage transformation. When the backup transformer is energized, it creates a new separately derived system with its own grounding electrode system and its own set of conductors. Sixthly, to further clarify the differences, let's consider some practical examples. Imagine a hospital that has a backup generator to provide power during outages. The hospital's electrical system is designed as an SDS. The generator is electrically isolated from the utility grid by a transfer switch, and it has its own grounding electrode system. This ensures that the hospital's critical equipment will continue to operate safely and reliably during a power outage. Now imagine a homeowner who has a portable generator to power a few appliances during an outage. The homeowner's electrical system is likely a non-SDS. The generator is connected to the home's electrical system through a power cord, and it relies on the utility grounding system. While this is a simpler and less expensive setup, it may not provide the same level of safety and reliability as an SDS. Seventhly, it's important to be aware of the relevant codes and standards that govern the installation and operation of SDS and non-SDS. In the United States, the National Electrical Code, or NEC, provides detailed requirements for grounding, bonding, and overcurrent protection in both types of systems. It's crucial to consult the NEC and any local codes to ensure that your electrical system is compliant and safe. Eighthly, one of the key advantages of an SDS is that it provides a clean and stable power source. Because the generator is isolated from the utility grid, it is not affected by voltage fluctuations, harmonics, or other power quality problems that may be present on the grid. This can be particularly important for sensitive electronic equipment such as computers, medical devices, and industrial controls. Ninthly, another advantage of an SDS is that it provides a higher level of safety. By having its own grounding electrode system, the generator is less likely to be affected by ground faults or other electrical hazards. This can help to protect both equipment and personnel from injury or damage. Tenthly, there are also some disadvantages to using an SDS. One disadvantage is that it can be more expensive to install and maintain than a non-SDS. This is because it requires additional equipment, such as a transfer switch and a grounding electrode system. Another disadvantage is that it can be more complex to design and install. This is because it requires a thorough understanding of electrical codes and standards. 11thly, in summary, the key differences between SDS and non-SDS are electrical isolation, grounding electrode system, transfer switch, and compliance with codes and standards. To determine if a system is SDS or non-SDS, you must consider the presence or absence of these key differences. 12thly, when dealing with generators and backup power systems, safety should always be the top priority. Make sure that your electrical system is properly designed, installed, and maintained. Consult with a qualified electrician to ensure that your system is compliant with all applicable codes and standards. 13thly, beyond the fundamental differences already discussed, it's useful to explore some advanced considerations regarding separately derived systems. These considerations often arise in more complex electrical installations, particularly in commercial and industrial settings. 14thly, impedance grounding is a technique used in some separately derived systems to limit the ground fault current. Instead of directly grounding the neutral conductor, a resistor or reactor is inserted in the grounding path. This reduces the magnitude of the ground fault current, which can help to protect equipment from damage and reduce the risk of arc flash. 15thly, another advanced consideration is the use of multiple separately derived systems in a single facility. In large buildings or industrial plants, it may be necessary to have multiple generators or transformers, each serving a different portion of the facility. In these cases, it's important to carefully coordinate the grounding systems to ensure that there are no circulating currents or other problems. 16thly, harmonic mitigation is also an important consideration in separately derived systems. Generators and transformers can be sources of harmonic currents, which can cause overheating, voltage distortion, and other problems. To mitigate harmonics, it may be necessary to install harmonic filters or to use special transformers that are designed to reduce harmonic generation. 17thly, surge protection is another important aspect of separately derived systems. Generators and transformers can be vulnerable to voltage surges caused by lightning or switching operations. To protect against surges, it's important to install surge protective devices or SPD at the generator and at other critical points in the electrical system. 18thly, power quality monitoring is a valuable tool for ensuring the proper operation of separately derived systems. By monitoring voltage, current, harmonics, and other power quality parameters, it's possible to detect and diagnose problems before they lead to equipment failure or downtime. 19thly, when designing and installing separately derived systems, it's important to consider the impact on the overall electrical system. The addition of a generator or transformer can affect the voltage regulation, short circuit capacity, and other characteristics of the system. It's crucial to perform a thorough engineering analysis to ensure that the system will operate safely and reliably. 20thly, let's delve into specific scenarios where understanding SDS and non-SDS configurations is paramount. Consider a data center where uninterrupted power is critical. Data centers often employ multiple generators and UPS or uninterruptible power supply systems to ensure continuous operation. In such a setting, each generator might feed a separate bus, creating multiple SDS. Transfer switches and grounding systems must be meticulously designed to prevent any disruption during a switchover. 21stly, in contrast, a small retail store with a single backup generator might opt for a non-SDS configuration for cost effectiveness. The generator would be connected to the store's electrical panel through a manual transfer switch, relying on the utility's grounding system. While simpler, this approach requires careful adherence to safety protocols to avoid backfeeding the grid. 22ndly, hospitals, as mentioned earlier, represent a critical application for SDS. The NEC mandates stringent requirements for essential electrical systems in healthcare facilities. Generators must be capable of supplying power to life safety equipment, critical care areas, and other essential loads. The separately derived nature of these systems ensures that any fault in the utility grid will not compromise the hospital's ability to provide patient care. 23rdly, industrial plants often utilize complex electrical distribution systems with multiple voltage levels and interconnected loads. Generators may be used to provide backup power to specific processes or to supplement the utility supply during peak demand. In these scenarios, the decision to implement SDS or non-SDS configurations depends on factors such as the sensitivity of the loads, the cost of downtime, and the complexity of the electrical system. 24thly, beyond these examples, it's important to recognize that the choice between SDS and non-SDS can also be influenced by regulatory requirements. Some jurisdictions may have specific rules regarding the use of generators and backup power systems, particularly in critical infrastructure applications. 25thly, furthermore, the selection of equipment, such as transfer switches, grounding electrodes, and overcurrent protective devices, is critical for ensuring the safe and reliable operation of both SDS and non-SDS configurations. It's important to choose components that are properly rated for the application and that meet all applicable standards. 26thly, let's explore the practical aspects of grounding electrode systems for SDS. The NEC specifies the types of grounding electrodes that are permitted, such as ground rods, ground plates, and concrete-encased electrodes. The size and spacing of the grounding electrodes must also comply with the NEC requirements. 27thly, in addition to the grounding electrode conductor, which connects the generator's neutral conductor to the grounding electrode, must be properly sized and installed. NEC provides tables and formulas for determining the appropriate size of the grounding electrode conductor based on the size of the generator's conductors. 28thly, bonding is another important aspect of grounding in SDS. Bonding refers to the practice of connecting all metal parts of the electrical system together to create a low impedance path for fault currents. This includes bonding the generator frame, the transfer switch enclosure, and any metal conduits or raceways. 29thly, when dealing with multiple generators in an SDS configuration, it's important to ensure that the grounding systems are properly coordinated. This may involve connecting the grounding electrodes of the generators together or using a common grounding electrode system. 30thly, let's shift our focus to transfer switches, which play a vital role in both SDS and non-SDS configurations. Transfer switches are used to switch between the utility power and the generator power. There are two main types of transfer switches, manual and automatic. 31stly, manual transfer switches require the operator to manually switch between the utility power and the generator power. Automatic transfer switches, on the other hand, automatically switch between the two sources of power based on the availability of the utility supply. 32ndly, the selection of a transfer switch depends on the application and the level of reliability required. Automatic transfer switches are typically used in critical applications, such as hospitals and data centers, where uninterrupted power is essential. 33rdly, transfer switches must be properly rated for the voltage, current, and short circuit capacity of the electrical system. They must also comply with all applicable standards. 34thly, installation of transfer switches must be performed by qualified electricians in accordance with the manufacturer's instructions and all applicable codes. 35thly, now let's examine overcurrent protection in SDS and non-SDS configurations. Overcurrent protective devices, such as circuit breakers and fuses, are used to protect the electrical system from overloads and short circuits. 36thly, the selection of overcurrent protective devices depends on the size of the conductors, the characteristics of the loads, and the short circuit capacity of the electrical system. 37thly, overcurrent protective devices must be properly coordinated to ensure that the device closest to the fault will trip first, minimizing the impact on the rest of the electrical system. 38thly, in SDS configurations, the overcurrent protective devices must be coordinated with the generator's protective relays to prevent the generator from being overloaded or damaged. 39thly, maintenance and testing are essential for ensuring the continued safe and reliable operation of SDS and non-SDS configurations. Generators, transfer switches, and overcurrent protective devices should be regularly inspected, tested, and maintained in accordance with the manufacturer's instructions and all applicable standards. 40thly, generators should be load tested periodically to ensure that they are capable of supplying the required power. Transfer switches should be tested to verify that they switch properly between the utility power and the generator power. 41stly, overcurrent protective devices should be tested to ensure that they trip properly under overload and short circuit conditions. 42ndly, documentation is crucial for the effective management of SDS and non-SDS configurations. Complete and accurate documentation should be maintained, including system diagrams, equipment specifications, test reports, and maintenance records. 43rdly, documentation should be readily available to qualified personnel for troubleshooting, maintenance, and future modifications. 44thly, training is essential for ensuring that personnel who operate and maintain SDS and non-SDS configurations are properly trained. Training should cover topics such as system operation, safety procedures, troubleshooting, and maintenance. 45thly, training should be provided by qualified instructors and should be updated regularly to reflect changes in technology and regulations. 46thly, let's circle back to the concept of separately derived systems, which are defined by the NEC as a premises wiring system whose power is derived from a source of electric energy or equipment other than a service. 47thly, a separately derived system has no direct electrical connection, including a solidly connected grounded circuit conductor, to supply conductors originating in another system. 48thly, sources of separately derived systems include generators, transformers, and converter windings. 49thly, the key characteristic of a separately derived system is that it has its own grounding electrode system that is independent of any other grounding electrode system. 50thly, the grounding electrode system for a separately derived system must comply with the requirements of the NEC, including the type and size of grounding electrodes and the size of the grounding electrode conductor.